All right, let's go ahead and get started here. I do want to point this out. You have just a front and a back to yours. That'll go over the basic shapes and everything. I am going to do a couple more problems when we get done. These are out of your textbook, so don't close your books and take off when we're done with that back side, all right? So this section is on graphing secant and cosecant, but I want to kind of explore where these come from so you know why they make the shapes they do, because the shapes are pretty funky, all right? So the reciprocal identities for secant and cosecant. Secant, let's see, secant is, now the way I keep this straight is in my mind, I always, if I see secant, I say sec cosine for some reason. That just keeps it straight for me. I don't care how you keep it straight, but secant is the reciprocal of cosine, cosecant is the reciprocal of sine. So this is 1 over the cosine of x, and this is 1 over the sine of x, okay? So secant, reciprocal of cosine, cosecant is the reciprocal of sine. Decimal approximation for each one of these. We talked about these before. This isn't an approximation, this is exact, so that's going to be 0.5. Correct me if I'm wrong, but that's about 0.7, and this we decided was about 0.9, right? You'll notice that each one of these fractions or each one of these decimals is between 0 and 1. So if I flip each one of them over, okay, it's kind of hard to flip a fraction over. But if I, flip a decimal over, but if I flip that fraction over, this one is 2. So the reciprocal of 1/2 is 2. If I do the reciprocal of radical 2 over 2, I'd get 2 over radical 2, which in order to make sense of it in what we typically see, we'd rationalize the denominator. So I'd have 2 radical 2 over 2. The 2's would cancel. This would be the same as radical 2, which is 1.4, right? Approximately. So if I did the same thing with this one, that's going to be 2 over radical 3. So if I rationalize the numerator, I end up with 2 radical 3 over 3. Throw that into your calculator. What do you get for the reciprocal of radical 3 over 2? What is it? 3.2? 1.2. Okay, 1.2. Okay. All right. And then these should be values that you can come up with reasonably quickly. Okay, we need the secant of pi fourths, so if we need to think of where that would be, that this is radical 2 over 2, radical 2 over 2, and this is 1. I'd need the secant of pi fourths. That's the r over the x. It's the reciprocal of the cosine ratio, so it would be 1 over this, so it would be the reciprocal of radical 2 over 2. Well, that would be this guy right here, so this is going to be radical 2. Is that all right? If it were 5 pi 6, 5 pi 6 is over here. This is 1/2. This is negative radical 3 over 2. That's a 1. Again, it's the reciprocal of the x coordinate. So that would be this expression right here, except for it would be negative. So this is going to be negative 2 radical 3 over 3. You doing all right with that? If I do the cosecant of pi 6, so here's what pi 6 would look like. I'm only going to draw the y-coordinate because the cosecant would be the reciprocal of the y-coordinate. So this is going to be 2. And then 2 pi thirds. Haven't drawn that yet. 2 pi thirds would be here, negative 1/2. Don't really care about that. We need to know that the hypotenuse, of course, is 1. And this is going to be radical 3 over 2. So the reciprocal of radical 3 over 2, we already talked about that. That's this right here, 2 radical 3 over 3. Okay, are there any questions there? Okay, just good reminders on how we find these, how we flip those over and stuff like that. And then a couple problems that might seem a little bit on the silly side. What's the reciprocal of 1/5? 1/10 would be 10. Reciprocal of 1,000, or 1,000th would be 1,000. What's the reciprocal of 20? 1/20th, and the reciprocal of 100? 100th, okay? So what happens to when we do the reciprocal of a number, the reciprocal has this effect. It makes big numbers small, and what does it do to small numbers? Makes them big. Now you'll notice that these three right here were small positive numbers, so the reciprocals were big positive numbers. These were big positive numbers, relatively speaking, so the reciprocals were small positive numbers. What if I put a negative in front of each one of these problems here? what happens to the reciprocal? It's negative also. We're not changing signs or anything. We're just taking big numbers, making them small, and vice versa. Any questions there? Okay, now this is kind of a weird question. Well, if the reciprocal takes big numbers and makes them small, what's the smallest number you can think of? 0. So what happens if you flip 0 over? Okay, it becomes undefined, or it becomes, well, what if we took a really, 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 really small number? Like a decimal, 4,000 zeros and then a 1, and we flipped it over. Makes it really, really, really big. Okay? So the reciprocal of 0 is undefined. There is no reciprocal of 0. Okay? But if we had to say it was approaching a number, it's getting really big, and what's the biggest number you can think of? Infinity. Yeah, okay? So the biggest number, or idea would be a better way to put it, would be infinity. So if you flip a 0 over, you're going to get something that's getting really, really big. So we'll call that infinity. Okay? This isn't mathematically correct, but it's the right idea. Okay? So just keep that in mind. Are there any questions on that starter stuff there? Okay. Would you neatly graph the cosine function from negative 2 pi to pi and label the function values in quadrant 1? Okay, so at least go from negative 2 pi to 2 pi, and then if you can label the function values in the first quadrant, that would be great. I mean, we've been going over this for a while, so hopefully this is just second nature. Starts at 1 and then goes down, back up, looks like that, and then on this side it would do the exact opposite. So we've got a graph that looks something like this. It says label the common function values in quadrant 1. If this is 0 and this is pi halves, that's quadrant 1. So this function value here would be 0. At pi thirds, it would be 0.9, wouldn't it? At pi halves, it would be 0.7. And at pi thirds, it would be 0.5. Remember, it starts at 1 and goes down to 0. Is everybody okay with that? Okay. Any questions? Sure? Okay, then let's do the next part. I'm going to slide this up so we can see that one at the same time. Oh, I forgot to do this. What's the domain? What's okay to plug into this cosine function? Negative infinity to infinity. It goes forever in both directions, right? What's the range? Whoa, what happened here? Negative infinity to infinity and negative 1 to 1. And it includes those, right? Okay. All right. You still see okay? Let me see if this will work. Give me 1 second. Sometimes it just does that. Let's see if we work now. There we go. Okay, so we're in good shape. Okay, now we're going to graph the secant. And we're going to do it using these values right here. We're going to use this graph, the graph of cosine, to make the graph of secant. So remember, secant is 1 over the cosine. So if I wanted to find the secant of 0, I want secant of 0, I could do 1 over the cosine of 0, right? Whoops. Cosine of 0. What's the cosine of 0? Cosine of 0 is 1. So what's the reciprocal of 1? 1. So let's put a point right there. Okay, now remember, this was radical 3 over 2, radical 2 over 2, and this was 1/2. So if I wanted the secant of pi 6, secant of 30 degrees, I could take the cosine of 30 degrees, cosine of pi 6, and what do I do with this number? What do I do? Flip it over, do the reciprocal, right? Well, what's the reciprocal of 0.9, or what's the reciprocal of radical 3 over 2? It was about 1.2. It was a little more than 1. So if I go to pi thirds, it's a little bit more than 1. It's about right there. Reciprocal of radical 2 over 2, because that's what it would be at 45. That was 1.4, wasn't it? So if I go to 45 degrees, or pi fourths, about 1.4. Reciprocal of 60 degrees, or pi thirds, it'd be the reciprocal of 1/2, so that would be 2. Okay, now, I need you to think about this for just a second. Everybody looking up here? Okay, now, right here, these cosine values get really, really small. So what happens if I take a really small number and do the reciprocal of that really small number? What do I get? So does everybody agree that these numbers are getting bigger and bigger and bigger and bigger? And they're just going to go off the charts here, right? So they're going to get really huge. What's the reciprocal of 0? Undefined, right? There is no number that represents the reciprocal of 0. So what we have there is we have a big asymptote. So let's take a good look here. If I take the reciprocal of these values in the first quadrant, and I do so I flip them over, I get the reciprocal, I get the secant of each one of those angles. I get this graph right here. I get these dots that'll be connected here in just a second. What happens if I do the same thing on this side? Okay, are the function values negative? No. If the reciprocal of these small positive numbers were these big positive numbers, these are still small positive numbers right here, right? So won't the graph look the same on each side? Won't it do something like this? And be shaped like that. Now, everybody looks at this and they say, well, that kind of looks like a parabola. And yeah, it kind of does. But is it? It's not. Okay, there are a couple reasons why it's not. If you were to graph this perfectly to scale, it's pretty flat in the middle. Okay, parabolas aren't flat in the middle. They've got a pretty pointy vertex to them. This is fairly flat in here. And this one goes till it's almost straight up and down. Okay? Not quite, but almost. It just gets steeper and steeper and steeper. Okay? The parabola continues going out. So it's not a parabola, it's just kind of a curved shape that looks a bit like one. Okay, so please don't call it one. Everybody good there? Okay, now, the rest of this is hopefully going to be pretty easy if you get this. If I take, everybody watching? If I take small positive numbers and I do the reciprocal of small positive numbers, I get big positive numbers. Does that make sense? Okay, that's it in a nutshell. In fact, that's today's assignment and next time's assignment in a nutshell. Okay, let's take a look at this one right here. What type of numbers are these? What type of function values? They're negative, and they're small negatives, right? Well, what's the reciprocal of a small negative number? A big negative number. The reciprocal of small negative numbers would be big negative numbers. Remember, if you flip it over, it doesn't do anything to the sign, it just does something to the size of the number. Okay? Let's take this one right here. What's the function value right here? Okay, the function value is -1. What happens when you flip -1 over? it's still -1, isn't it? Flip that over, you get 1 over -1. It's still -1. So let's come down here and let's put a point at -1. And this is a 0. Reciprocal of 0 is undefined, so let's follow that down here. Let's put an asymptote here. Reciprocal of these small negative function values is going to be huge negative function values. So it looks like this. Okay. Any questions? Okay. These are small positive numbers, right? What's their reciprocal? Big positive numbers. So it looks like this. This function value right here is 1, so its reciprocal would be 1, so it looks like this. What about over here? Those would be big negative numbers. So again, here's the 0. We're going to have an undefined point on the graph right here, so it's going to have a vertical asymptote. And we'd have a graph that looks something like, I won't draw the whole thing so it doesn't get in the way, like that. And then you can probably guess what this piece would look like. It would look like that. Okay, there's the cosine. Everywhere it's 0, we've got a vertical asymptote. Everywhere it's +1, the secant is +1. Everywhere it's -1, the secant is -1. So if this is negative here, we have this branch pointing downward. If this is positive here, we have this branch pointing upward, downward, upward, and it just follows that pattern. Any questions there? Okay, I'll erase that. This is one cycle. We'll call it one fundamental cycle. So these would be the key points on this graph. Okay, if you were going to graph one cycle, you'd have to graph this branch going up and this branch going down. Any questions there? Okay, so let's fill in this box over here. It says, what is the period? How long does it take to repeat? Well, let's think about this for just a second. If this was 0, and this is pi halves, and this is pi, and this is 3 pi halves, and this is 2 pi, and this is negative pi halves. We had one cycle from here, oops, to here. So what's the period? 2 pi. Since this is built from the cosine graph, if the cosine graph has a period of 2 pi, then this should have a period of 2 pi. Domain. What numbers are okay to plug in? Or it might be easier to say, are there any points that don't work in the secant function? That's the range. Okay. Are there any points that are not in the domain? Negative pi halves, 3 pi halves. This one would be negative 3 pi halves. Okay. So here's how you state something like that. Rather than listing all of them, we do something like this. We say all the x's except for, pick one of these, pick any one you want. I'm going to pick this positive one right here. The first place that's not in the domain is pi halves. And then how far do I have to go to get to another asymptote? How far is it between pi halves and 3 pi halves? Pi. So we do plus k pi. And k is any integer. So that accounts for the fact that if it's positive, we go 1 pi, 2 pi, it repeats every pi units on that side. If it's negative, then we go to the left. We're just skipping every pi units to get to a vertical asymptote. Any questions there? Okay. The range, what y values do we get out? Okay, everything except, so from negative infinity to infinity, blow that up. From negative infinity to infinity, y not equal to, negative 1 to 1. Now, did I do that right? Should I have square brackets or open brackets? They should be open because I actually hit 1 and negative 1. Okay, so that's going to be open. Okay, any questions? Okay, now on this one, okay, I'll let you get away with 2 key points as long as the asymptotes are right. But we should be able to do these 6 points. So let me show you where they are. We should be able to do that one and that one. That ought to be a piece of cake. This is 0, 1. This is pi, -1. At the very least, you've got to be able to label the very bottom of this one and the top of that one. Now, the most convenient other points to graph, because they have nice function values, are this one right here and this one right here. And that was at 60 degrees or at a little less than pi half, so that's pi thirds, 2. This would be negative pi thirds, 2. So there's got to be one here and one here. Now let's think about how this works. Okay, there's some symmetry going on here. I went over pi thirds this direction and over pi thirds this direction. So from the center of that branch, I'm going to go over pi thirds. Where's that going to put me? Say 4 pi thirds. It is 4 pi thirds. That's amazing. Okay, so 4 pi thirds, -2. And this one's going to be, if I subtract pi thirds, this is going to be 2 pi thirds, -2. So those are the 6 key points. Now we labeled them over here. I'm not going to write them there. And then we want to know where the asymptotes are. So the asymptotes are at all those places that don't work in the domain. So we're going to write this same list down again. We're just going to say, here are the asymptotes. They're at x equals. Give it a place to start. Let's say it starts at pi halves. And then say how often it repeats. So we say k pi. Nice. Any questions? Sure? Yeah.
Where again do you get the pi from that? Where you get the...
Because this is the first asymptote at x equals pi halves. And then I want to know, how do I get from one that I have to the next one? Because they're all equally spaced. So how far is it from 3 pi halves to pi halves? It'd just be pi. Anything else? Sure? Okay, then the next one should be pretty darn easy because it's the reciprocal of the sine graph. So I'm going to do this really quickly. If you don't want to write this down, you don't have to. There's a page in your book with all the trig functions on it. But this is the basic idea. So I'd almost rather you watch and just make sure you've absorbed this and you understand where these come from. So sine starts at 0 and does this. So our graph looks something like this. That's the sine graph. And I'm not going to label a bunch of stuff on here. I am going to write down what the domain is. It's from -infinity to infinity, and the range is from -1 to 1. You can plug in any angle you want, and it will always spit out a number between -1 and 1. Then I'm going to come down here, and I'm going to graph what its reciprocal would look like. So if this is the original function, let's figure out what its reciprocal would be. So wherever this hits a 0, what do I have? What feature do I have down here on its reciprocal? I have an asymptote. So I'm going to do an asymptote here, 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 and so forth. These are small positive numbers. What do I get when I do the reciprocal of small positive numbers? Big positives. Smallest it gets to be is 1, because that's the biggest that gets. Reciprocal of small negatives, big negatives. So it's going to look like this. Okay, not exactly like that. Like this, and like this. Okay? Any questions? Okay, watch please. Where is this asymptote? X equals 0. Where's this one? It'd just be pi, wouldn't it? This goes from 0 to 2 pi for one cycle, so that would be at pi. So this is 0 pi, and this would be at 2 pi. This would be at negative pi, and this would be at negative 2 pi. So if I were to say you know, what's one fundamental shape here? That branch and that branch. Notice this is kind of nice because they're all on the positive side. And if I were to label a few of these points, this is exactly the same shape that we just graphed. It's just been slid over a little bit. So we should be able to label a couple points on here. This one right here would be at pi halves, comma, 1. This one would be at, it's right in between pi and 2 pi, so that would be 3 pi halves, comma, negative 1. Now listen carefully. How far did we go on the secant graph to get to this other point right here? How far was it from the center? It was pi thirds. So if I add pi thirds to this is why we've got to be good at fractions. That's why we spent so much time on this in chapter 1. Pi halves plus pi thirds is 5 pi sixths, comma 2. Pi halves minus pi thirds would be pi 6, comma 2. And then I'm not going to take the time, but you could label those other guys right here. Okay, are there any questions? Sure? Okay, then let's take a look at the period. What is the horizontal distance needed to repeat this shape? 2 pi, just like it was on secant. The domain. You took this graph and squished it onto the x-axis to figure out what x's you could plug in. You can plug in any number you want except places where we've got an asymptote. So we're going to say x is not equal to, what's the most logical place to start here? 0, and then we put plus, so tell it where to start and then how often to repeat that asymptote. We just put k pi because it's pi units in between. Yeah?
Why wouldn't you just put k pi?
You can put k pi. This is just for symmetry. Okay? When you're writing something down like this, you do it this way every time. Write down where to start, give it a starting point, and then write down how often it needs to repeat. Okay? Since it starts at 0, Austin's right, you wouldn't have to write 0. You could just write k pi. Questions? Range? Negative infinity to infinity, all the y's except for the stuff in between negative 1 and 1, just like it was before. This should look familiar, right? It's the same shape, it's just been moved over. And then the asymptotes, we'd write down that list again. I'll write k pi. Any questions? Sure? Okay, grab your calculator then. Okay, those are the basic shapes. We're going to go through and we're going to transform those a little bit. But you've got some problems on your assignment that are like this. It says secant of 1.56. Secant of 1.56. So first of all, if you're going to type this into your calculator, what would you need to make sure of? It better be in radians. So make sure your calculator's in radian mode. Now, does your calculator have a secant button? It doesn't. Okay? So you need to remember the identity. The secant is 1 over the cosine of that same thing. So this is going to be 1 over the cosine of 1.56. And what do you get? What is it? 92 point what? 36, whatever. It's a big freaking number, right? Okay. Any questions? Okay. 1.56 is pretty close to 1.57. Whoops. A few too many decimals. We certainly don't need that. Which is about pi halves. It's just a little bit shy of pi halves. So if we were doing the secant of a number that's just a little bit shy of pi halves, we just figured out that the function value would be 92. That's 1 right here. Think about how far off the charts that would be. That would be way up there, just because we're just shy of pi halves. Does that make sense? Looks good on the graph? Okay, any questions? Okay, you may need just scratch paper or something like that. We're going to try and do 3 more problems here. Okay, once we know what those basic shapes are, you can do the same thing that we did before. You can slide it up and down. You can have a phase shift. You can change the period. And this isn't really an amplitude, but it is a vertical stretch or shrink. Okay? So these four things do exactly what we figured out they did on sine and cosine. So we should be able to make some transformations of this. So we're going to do this one right here. We're going to look at number 29. So 29 is 2 secant of x. So what I want in my head is, what did secant look like? Secant was, and this is a bit of an oddball, secant is the one that looked like this. There's one fundamental shape. This is negative pi halves. This is pi halves. This is 3 pi halves. This is 0, 1. This is, help me out here, pi negative 1, right? Everybody good there? Okay. What does the 2 do to this graph? Vertically stretches it, right? It makes all the coordinates twice as taller. It makes the graph steeper than it used to be. Does it do anything to any of the x coordinates? It doesn't. So we're going to take this graph, and we're going to take this point, and we're going to move it up. So we're going to start at 2. We're still going to have an asymptote at negative pi halves, and at pi halves, and at 3 pi halves. This one would be right here at negative 2, and I'm going to have a branch that goes up like this, and a branch that goes down like this. Now, this one is easy to label. Will you label that one right there? Label both those points there. This one is 0, 2, and this one is pi, negative 2. Okay? And could we write down where the asymptotes are? The asymptotes are at, x equals pi halves plus still k pi, right? That's it. Any questions? Okay. Let's see. What would this do to the graph? Change the period. What would the new period be? 2 pi thirds. Okay. So if you were going to do that one, okay, now let's think about this for a second. If the period is 2 pi thirds, okay, we're still going to have a shape that has an asymptote here, an asymptote here, and an asymptote here. Okay, but it was shrunk by a factor of 3. So if the old period was 2 pi, and we divide everything by 3, we're shrinking all the x coordinates by 3. So if this one used to have an asymptote at negative pi halves, we'd be sliding that one back this way. So that would be at negative pi 6. Where would this one be? Pi 6. Oops. So this would be at negative pi 6. This one would be at pi 6. Okay. How far is it in between these? Pi thirds. It's exactly half of the period. So I'd add another pi thirds. Where would this asymptote be? Very good. It's at pi halves. Because from here to here is pi thirds. From here to here is pi thirds. How far is it from the beginning of this shape to the end of that shape? 2 pi thirds. Okay. Does that make sense? Okay. Skip down here. Take a look at 57 through 64. It says find the equations of the vertical asymptotes. So that's basically what I was showing you right here. This is how you do that. Find out where they are. And if I were to write this down, if I were to write an equation for these asymptotes, I give it a place to start. Which one do you want to start with? Pi 6 plus k times, how often does it repeat? Careful, how far is it in between here? Pi thirds. It would be pi thirds there. Okay? All right. Any questions? Okay, take a look at these guys right here. These are all cosecants. So they're the other shape. Cosecant, again, it's actually kind of the nice one because it starts here and here. It's all between 0 and 2 pi, and that one would be at pi. What's that going to do to the graph? Vertical flip and a stretch. So that one's going to look something like this. Stretched and flipped over. See how that's twice as tall as it used to be and flipped over? Okay. Would it change where the asymptotes are? Nope. Okay. All right. You will have to spend some time thinking about these because the arithmetic can be a little bit tougher than we did with sines and cosines, but that's the idea. Okay? Have a great day. See you tomorrow for the quiz, and any questions you've got on these. It would be great if you got started so we could go over questions on these.